Here's an example of matching polar equations with polar graphs, getting to some slightly funkier graphs perhaps than we did before. Here's the four functions: 2 cosecant theta, cosine theta over 4, 3 plus theta, and sine 5 theta. These are all, they really should be r equals here. My bad. The computer doesn't require me to do that, but I really should. So they're all r equals these guys. Okay. And here's 4 graphs that are going to match with those things. So let's see how we could do this. Well, we can look at the qualitative features. We can always start plotting points, but it's a great opportunity to talk about the qualitative features. Well, you can either look at the pictures and see if there's anything that strikes you qualitatively in terms of symmetries, or when things go into the origin, or any kinds of the qualitative stuff we looked at in the other video. Or you can look at the functions. I think most people tend to look at the pictures first. And I think my eye is drawn to this one first. This is maybe the most familiar of all these. It's a 5-leafed rose. Doesn't really look anything like a rose, but it's a flower. It's got 5 leaves. It's strongly suggestive of this guy. Let's see if we can make that a little bit better in terms of a reason for matching. So the claim is that D matches 3. And we know that sine r equals sine 5 theta will have a 5-fold rotational symmetry. Okay, because we can add 2 pi over 5 2 pi over 5 to theta and not change r. That's really good to know. It'll also have it also has a y-axis symmetry, because I can put in pi minus theta. If you check, pi minus theta also works as well. If you replace theta with pi minus theta, quick calculation shows you that works. Then this has a y-axis symmetry. So that's definitely good. We could also even check even more, like this. We could look at the angle at which it comes into the origin and check that's where sine 5 theta equals 0. Let's do that. Let's set sine 5 theta. It's kind of overkill since we're pretty sure. But let's set sine 5 theta equals 0. Then 5 theta is going to be k pi. And so theta, whoops, is going to be k pi over 5. So in other words, it's going to start at pi over 5, and then it's going to be 2 pi over 5. Now those aren't particularly familiar angles, but pi over 5 is between pi over 4 and pi over 6. Yeah, that looks plausible for this first time after 0. Oh yeah, it starts at 0. So the first thing is simply that it comes out of the origin along the theta equals 0 direction. Then it comes back in, looks plausibly between pi over 4 and pi over 6. Then the next one up here, 2 pi over 5, yeah, that's almost pi over 2. And then 3 pi over 5, that'll be a little bit more than pi over 2. That totally makes sense. Okay, so lots of reasons those match. Okay, so we believe that claim, I think. Let me insert it a little bit above here so we don't run out. Claim, let's see. What about this guy? This is different because it's not a closed curve. It keeps going out and out and out, and it does not repeat. There are different r values for the same theta. That's very much not true for this curve or even for this curve. So let's see. It should be a function of theta that does not repeat. Well, hey, this is the only one that doesn't have a periodicity. Okay. And let's look what happens. As theta increases from 0, it's going to start out r at theta equals 3, and then bigger and bigger and bigger. And indeed, this is something, as I wind around and theta increases, I get bigger and bigger and bigger r. And for the same direction, like 0, 2 pi, 4 pi, 6 pi, I actually get different r values, and so it does not close up. Okay, so that's going to say C is 1, not periodic, and in fact it's an increasing function of theta. Now one thing that's a little important to note is that to make this not really confusing looking, I specifically didn't put in theta being negative. So this actually, to be really careful, this is really where theta, oops, is greater than 0 as well, or greater than or equal to 0. Okay, if you put in negatives, it kind of have another spiral superimposed on it. It's just kind of ugly. Okay, What about the other two? Okay. Well, let's look at these. Cosecant theta. There's something very important about cosecant theta. And that is, let's put in a little note. The note is that cosecant theta, or 2 cosecant theta, math mode, is unbounded. It goes off to infinity, or it gets arbitrarily large. It's like tangent, cotangent. If you look at the Cartesian graph of that, it blows up. And so it can have these huge values. And that's suggestive that it's a better match for this than for this. This guy always stays within 1 unit away from the origin. This thing starts at 2 units away here at theta equals pi over 2 and goes, looks like it's a straight line. Looks like it's going way off this way and this way. Okay, so that's suggestive that it's going to be a match here. This is one where it's actually really good to break out the algebra to be really sure. This one is surprisingly easy to convert to Cartesian, because this is 2 divided by sine theta. And so it's r sine theta, oh my goodness, that looks familiar, equals 2. That's y equals 2. So even though it looks weird in the polar form, it's actually secretly an incredibly simple Cartesian equation. So usually we can't do this. We can't convert it to a simple Cartesian. But here, we really should be able to. We should be able to look at one of these equations and convert it to y equals 2. And indeed, this was the one. Okay, and that combined with the fact that it's the only one that runs off to infinity, besides this one, which we were already pretty sure of, being 3 plus theta. That's a good match. Okay, so so C is going to be 2. So C is 2. Okay, and then the last one, well, by process of elimination, it looks like B is 4. Can we actually do that without just process of elimination, which is pretty shaky? Well, the thing about cosine theta over 4 is that if theta, for example, is 2 pi, we expect, like in this curve, it repeated. We got back to exactly the same r value. But here, we don't, because theta over 4 is just up to pi over 2. We've experienced this a bit when we're solving trig equations. When we have weird multiple angle kind of things in trig equations, we have to be careful about that. Our intuition about when things repeat isn't going to be correct. So here, as I start here, it looks like we might start here. Let's see, let's check that. If theta is 0, cosine 0 is 1, aha, yeah, it looks like it starts here. What happens is it goes around, and in one full loop around, I actually don't get back to where I started, because the theta over 4 has only cranked up to pi over 2. In all that trip, the cosine starts at 1 and ends up at 0. Because cosine of 0 is 1 and cosine of pi over 2, not 2 pi, is 0. So that's what allows this to have this funky shape where in any particular direction, let's see how many things there are. 1, 2, 3, 4. That's a good hint that this theta over 4 is a match. And that would probably be good enough to do this. This is a pretty complicated graph. Oh, one other thing though. Also, it's x-axis symmetric. Ooh, that doesn't work. And that's because if I put in cosine of minus theta over 4, God, I keep confusing my pi's and my thetas. Because cosine is an even function, that is the same as cosine theta over 4. So if my old r value was cosine theta over 4, my new r value is the same. And so that's what gives us this x-axis symmetry. And so that's good. It's really the only graph that is x-axis symmetric. So apart from the sophisticated analysis about going sort of 4 times around before it loops up again, before it closes up, this is a simpler way to check. Always look for those symmetries. Okay.